Welcome back again. We continue talking about applications of cross product, and we want to do some application problems. We have a range, and we have a bolt. We want to tighten the bolt, and for this purpose, we are applying a force of 50 newtons. Okay, so right now, the magnitude of the force exerted is 50 newtons, and it is applied to the end of a 20 centimeter range. So this range we have, this distance is 20 centimeters. That's the length of the range. And this force is making an angle of 30 degrees with the handle of the range. So the angle that it makes with the handle of the range is 30 degrees. So obviously the remaining angle would be 60 degrees. That's what is described in the question. We want to find the torque on the bolt at the other end of the range. That's what we want to calculate. So we want to find this torque vector. So first of all, we're going to use the formula for the torque, which is the magnitude of F times magnitude of R times sine of angle theta. That's the magnitude, comes from the definition of cross product. And the force is 50 newtons, and R is the length of the lever arm or the torque arm, and that is 20 centimeters, but we have to convert that into meters in the SI system of units. So that becomes 0.2, and the angle would be the angle between the R and F vectors. So vector R is this way, and vector F is this way. And the question is, what is the angle that these two make with one another? So R that way, F this way. So I would say that angle is 30 degrees. It's not that difficult to draw them tail to tail, because think about it, if you extend this, these two angles are opposite angles, and these two angles are also opposite angles, so 30 degrees and 60 degrees. So sine of, we have to write 30 degrees. So using a calculator, we will find out the answer would be 5 Newton meters. So the unit of measurement Newton meters, magnitude of the torque is 5. And now we need to find the direction using the rule that we have learned, the right-hand rule. So we have R that way, curling your fingers towards F through an angle which is less than 180 degrees. It shows the direction of the thumb is into the page, right? So we're going to say that tau points actually into page. That's what we got, points into page. So that's the direction. So I'm going to write down here into page. And now this is complete, except that I just changed the symbol for the magnitude because this is the vector itself. So the magnitude was 5, but right now, including the unit, I'm just talking about the vector quantity itself. So that would be the torque vector in this example. Then what is the maximum torque that can be achieved by a 50 Newton exerted force on this range, and how can it be achieved? Well, basically they're looking for tau sub max, so maximum of tau, maximum torque. Well, force is fixed. You're exerting a certain amount of force, and the distance is just 0.2. That's the size of the lever arm. You can't change it. You can't make the range bigger. So the only thing here that makes a difference is the angle, basically. So when is sine theta maximum? Obviously, maximum value of sine theta is 1, and that happens when the angle is 90 degrees. So tau max would be magnitude of F times magnitude of R times 1, okay? And that is when sine theta is equal to 1. In other words, theta is equal to 90 degrees. So if theta is 90 degrees, if the angle that R and F vectors are making with respect to one another is 90 degrees, if the two vectors are perpendicular, in that case sine theta would have a maximum value of 1, and as a result, the torque tau would also have a maximum value. And in this case, we can calculate the maximum value. It would be 50 and times 0.2, which would be, of course, 10 Newton meters. So the two vectors must make an angle of 90 degrees, and the maximum torque is 10 Newton meters. If you make the force at an angle, in this case it's 30 degrees, for example, then the amount of torque is less than the max value of 10 Newton meters. So if you want to have really maximum effect on the bolt, you have to exert this force at a 90-degree angle. Otherwise, you're wasting a little bit of your power, I should say. Another example about applications of cross products, other than the torque, is when we find the angle between two vectors, whether 2D or 3D. So let's say we have two vectors, and one is vector u, and that is 4, 5, 2, and another vector is 3, 2, 7. So how do we find the angle between these two? Well, we can use cross product. Okay, we can say u cross v is equal to, so first of all we can find the cross product of them. So 4, 5, 2, 4, 5, 2, or any method you want you can use to find the cross product. I'm using this crisscrossing method. 5 times 7, 35, minus 4 is 31. And then 2 times 3 is 6, minus 28, it's negative 22. And then 8 minus 15 is negative 7. So 31, negative 22, and negative 7 is the result of the cross product of these two vectors. But then, if you remember the cross product formula, we said that u cross v is actually magnitude of u times magnitude of v times sine of theta. So if you solve for sine theta, then sine theta would be the magnitude of cross product divided by magnitude of u and magnitude of v. So when you take the inverse sine of this big fraction, then that gives you technically the measure of angle theta. So what I'm going to do, I'm going to find the magnitude of this cross product. So that would be square root of 31 squared plus negative 22 squared, negative 7 squared. That's the magnitude of the cross product. In the numerator, in the denominator, I should have taken the inverse sine. So this is inverse sine of that big expression, which is equal to angle theta we're looking for. So magnitude of u would be 16 plus 25 plus 4, and the other one would be 9 plus 4 plus 49. So all we need is a calculator to figure this out. And if you use a calculator, I believe you get 47 degrees. Okay, so the angle would be 37 degrees. This is how we can apply the cross product to find the angle between two three-dimensional vectors. We could have got this using the dot product as well. Not that, no, we could, and I suggest you try to see if you can do it. Other applications are the volume of a parallel pipette, which I think I probably mention it in another lecture because the board is full right now. So for now, this much is enough. Thank you.